So we are fortunate to have today Fred MacKintosh. Fred is an old friend of this department. He spent, I don't know, half a year or a year on sabbatical.
He was off and on for like 2 years, right?
Okay.
Because Miriam was here
Okay.
at the time. So.
Okay, so he is one of those theoretical physicists who thinks very deeply about physics of life, and he achieved many seminal results in this direction. For instance, my favorite story of his is he showed in a very direct way how you can distinguish between something that is live from something that is dead by looking at detailed balance principle. If it violates detailed balance, it's alive.
So you invented the life meter.
A more time. By the way, Dave, where are you?
I'm writing to him right now. He's busy in his office.
Oh, Dave Pine. I remember the discussion of a mortometer back years ago when we overlapped briefly at Exxon.
Very good.
That was having to do with light scattering.
Okay, all right. So that will come in the future, I guess, after the talk. So I'm not sure what Fred will tell us today about. Will it violate detailed balance or not? But I hope.
No, it's not going to be very non-equilibrium today, I'm afraid.
Okay. Still, it will definitely be interesting. Well,
thank you very much. It's a pleasure to be back here. New building. This is my first time in this building. I did know you had moved, but my time was about 10 years ago in the other building. So what I wanted to do in the next 45 minutes or so is try and convince you that a very mundane, seemingly boring system can exhibit surprisingly rich physics, and specifically phase transition and even critical phenomenon behavior. So that's my goal for the day. I'm not sure why that thing is in the way. It seems to be popping up and disappearing. Okay, but so huh?
It is alive.
Well, it has at least a mind of its own. Maybe that's AI. There's at least 3 reasons to work at the interface between physics and biology. You can use physics to learn new biology or to solve biological problems, or you can think about what biology can do for physics. If you like, that's the approach I will take, which I will attribute to, if I've got a mouse here, Stan Ulam, slightly misquoting him. So he probably would have said mathematics rather than physics here, but he was basically saying, ask not what physics or mathematics can do for biology, but what biology can do for physics. That's the approach. That's the approach I will take. I said there's a third way. The other one's making money. I haven't figured that one out. But at least this is behind a lot of our thinking. And we tend to think of these living systems as challenging examples that pose new questions that we wouldn't have thought about thinking about dead materials. Okay? Even though the materials for today are going to be mostly dead. So that rather mundane material I want to focus on is actually tissue mechanics. Like our skin. So a key player in the mechanics of that is collagen. It's the single most prevalent protein in our bodies. And it exhibits, that's not an image of collagen, that happens to be blood clot, fibrinogen network, similar, but the picture is a little bit more colorful than what I have for collagen. But these are fibrous networks that superficially might be reminiscent of other polymer networks, but they're very different and challenging in their own ways to try and understand. And we've been largely lacking over the last, over most of last few decades, lacking good theoretical predictive approach to deal with those systems, such as we have for more flexible polymers. And that's the kind of thing I want to tell you that we can make a little progress with, thinking about things in terms of the phase transition. Okay, so along the way, of course, I'll be mentioning the work of a number of current and recent members of the group, as well as a lot of experimental collaborations over the years. I've been fortunate to work with some excellent experimental groups, also willing to ask what biology can do for physics, okay? Like Paul Janme, who's just down at UPenn. I'm sure you've had him through here at some point. Dave Waits, you must know. I won't happen to mention any data of his today, I don't think. Gijs Koendrink in the Netherlands, in Amsterdam, now Delft, is a longtime collaborator as well. Okay, so the systems I want to focus on, there's something slightly different, having zoom on with my keynote here, so that hopefully it doesn't screw up some of the timing. But so this is a beautiful image of collagen on the left. It has my little cartoon images of cells, so ignore those. I wasn't going to show you those immediately. The image of the collagen is the real thing. But you know, if you happen to have any background in synthetic polymer systems, polystyrene, poly whatever, this is a pretty weird image. It might be a network, but there's nothing like a random coil, so you should forget about that if you've ever run across that. If not, don't worry about it. It's also on a huge scale. So rather than a monomeric unit being a simple molecule or atom, these collagen fibers, collagen type 1, form really thick fibers. The image you're seeing here is of fibers with a diameter around 100 nanometers. So they're approaching a macroscopic athermal elastic rod at that point. And that is actually that poses one of the reasons why these have been a little challenging to think about, in contrast with flexible polymer systems where we can use a lot of the machinery of statistical mechanics, okay? They're athermal, and if you like, their properties have to do with quench disorder rather than, let's say, fluctuations exploring a range of configurations and therefore with some self-averaging. They're also composites. They're highly nonlinear elastic materials, and that's basically what I'm going to start with. But already, as I said, the length scales involved are rather different from flexible polymer systems. And this little sketch of cells on the left is meant to indicate that something of order 10 or a couple tens of microns would fit in one of the pores here. Almost. Something similar happens with blood clots. Again, I like that image, false color image from a UPenn group. But it shows, again, the scale of a 7 micrometer red blood cell there. Anyone happen to know what the magenta things are? Platelets, thank you, exactly. So those are cool, active little elements in that system, but I won't talk about that. Okay, so they're composites. That's another thing to bear in mind. But let me go back to classical physiology work from 50 years ago or so. This is an experiment you can do right now by just pulling on your earlobe. And you'll notice, and you know from everyday experience, that we depend on this, that our tissues have a property, they're not linear elastic, that's a very good thing. And in particular, they stiffen as you deform them, if you like, making them inherently stable or self-stabilizing, if you like. As you deform them, they become less deformable. And in terms of force versus extension, this is just a section of tissue under simple extensional strain, as it happens. I'm going to focus mostly on shear strain, just because it's volume preserving and the kind of thing that's experimentally more easily accessible. But much the same thing happens. We don't see a Hookean response. This is not just a linear relationship between force and extension. it's highly nonlinear, and its compliance is going down. So in other words, as you load a tissue like your earlobe, it can bear a stress far in excess, literally a couple of orders of magnitude in excess of what the linear shear modulus would lead you to believe. Okay? So that's important. And I want to convince you that you can understand that effect in terms of a phase transition. There's no obvious distinct phases here, however. Okay? So it's not directly obvious. Now, in this 50-year-old physiology work, and this is the part that might get cut off with that thing that I can't remove. I really don't know why that is there. What Feng did actually was plot not force versus extension alone, but the derivative of force versus extension, not versus extension, but versus force. So it's the derivative of this function versus the function, and he gets a straight line, an approximate straight line. That suggests an exponential stress-strain relationship. Okay. Now that can't be a fundamental constitutive relation for a material that at least admits a linear elastic regime, and these do. So hidden down here is some different behavior, and up at very high stresses something else would happen, but it's already a little surprising. Okay, so we'll wind up characterizing the mechanics frequently in terms of this derivative of stress. Not necessarily versus stress, but versus strain. So how would one start to approach this system? Well, I kind of like going back to 150-year-old work by Maxwell. Of course, physicists know Maxwell first probably for electricity and magnetism, but he was as much an engineer as he was a physicist, I would argue. And mechanical engineers know him for this work, studying the stability of macroscopic objects. This is a modern bridge, but it shows this classic Warren truss structure, which you'll recognize from a lot of bridges, particularly here in the Northeast, right? Don't tend to see it so much elsewhere in the US, but anyway. What Maxwell did is he was arguing what are the minimal stability conditions for such an object. And rather than go through a regular structure like this bridge, let me jump forward to a disordered structure. Let me see if the mouse works. Ah, yes, it does. Okay. So what this image is showing is a piece of a more random network-like configuration where nodes shown in red are connected to each other by Hookean springs, just central force interactions between them. Keep it simple. That was indeed what Maxwell was looking at. And so in this two-dimensional picture, each of these nodes has 2 degrees of freedom representing the 2 axes along which they can move, okay? In 3 dimensions, it would have been 3. So there's 2 degrees of freedom per node. Obviously, when you want to build something, you connect things together, right? So as you connect the structure by adding these Hookean springs, it can become stable if you connect it enough. What is enough? Well, that's where this counting argument comes in. Notice that the node I was just pointing at is 4-fold coordinated. It's connected to 4 neighbors. Every connection is a constraint. So what Maxwell did is he said, let me take the degrees of freedom and subtract off the constraints, and what I'm left with is the remaining freedom. And so if I'm connected to 4 neighbors at that node, that's not 4 constraints per node, because each connector is connecting 2 nodes. It's 4 half constraints. So that's 2 constraints. That system is just barely stable. Disconnect any one of those bonds, and it'll be floppy, at least at some level. Connect it anymore, and it won't change whether or not it's stable. Okay? You might change a modulus or a rigidity for the whole structure, but you would do it only quantitatively, not qualitatively. Okay? So by the way, when I talk about rigidity, without talking about a modulus, I literally just mean, does it have a finite modulus or not? Okay, so it's a qualitative distinction. Okay, so what does that argument tell us about systems like these? This is collagen on the left, another nice image. This is actually, oh, I lied. This is actually from Dave Waite's group. collaboration a few years ago with his group. This is an image from cytoskeletal network of actin fibers. So this is a bit more about what controls cell mechanics. But does this argument in any way inform us about the stability of these systems? Well, not really, because if you zoom in on the collagen, what you'll see, and this is not this image, but it's my kind of microscopy I was showing you before, you'll find threefold branch points and fourfold crossing points. So the connectivity described by that local coordination number, which I argued in 2 dimensions should be 4 for a stable structure. In 3 dimensions, it would be 6. The connectivity of these systems is somewhere about 3.5. In fact, people literally measure that for collagen from images and come up with about 3.5 average. So that's well below the isostatic point, actually so that stability point is known as the isostatic point, either in 2 dimensions or 3 dimensions, especially 3 dimensions, where it's 6. Yes?
How do you know from a 2D image that they're, I mean, how do you count?
Very good question. This is part of the challenge. So they estimate connectivities because from even confocal microscopy, you can't really tell whether 2 things are connected. But from this image, it's pretty clear that you can't have a connectivity of 6. Okay, the connectivity will be below that. But you're raising a good point. It is challenging to come up with a precise number there. So it is a little bit of an estimate. Right, so seemingly, this says that this Maxwell picture doesn't tell us anything about the stability of the systems. And I will remain, I will not convince you otherwise, okay? That is true. However, it's still a very useful starting point to think about the mechanics of the systems, okay? So, it seems that these systems should be floppy, but of course what's left out of this picture, these were Hookean springs, what's left out of this picture is anything like a bending rigidity of these fibers, and they do indeed resist bending. More on that as we go along.
Also inextensible.
And inextensibility. Oh, actually, that's an interesting, yeah. So that's subtle. So fibrinogen networks, these blood clot ones I told you about, they're remarkably stretchable, easily stretchable fibers. They don't satisfy Euler-Elastica conditions for, let's say, the stretch modulus relative to bend modulus. Collagen does, though. Okay. At least seems to within error bars of experiments. But you're raising a good point. Extensibility will not be so relevant. Extensibility or not will not be so relevant for what I'm talking about because the strains are going to be relatively low. And you'll first engage the bending and transition towards stretching. That'll be actually the transition that I'm getting at. Okay, so back to Maxwell's picture. High coordination, stability, low coordination, floppy, non-rigid structures. It's not just that there's a boundary between these two, it's a genuine phase transition. That's another thing which one can study. Happens to be second order like critical, which is interesting. But back to the systems we're interested in, they're down here. So this modulus here doesn't tell us anything, or Maxwell's mechanism, if you like, doesn't tell us anything about their stability. However, and so that picture here should look, well, to my eyes, being a sort of stat mech person, that looks a little bit like magnetization as a function of temperature, okay? So let me just remind you of ferromagnetic behavior, where if you cool down something like iron below the Curie temperature, you get a continuous growth with interesting behavior, quantitatively interesting critical behavior here, this transition toward a ferromagnetic phase, okay? So to make an initial analogy between the thing we're interested in, which is the stability or modulus of these networks, and magnetization, I will ultimately tell you to forget that analogy, because it's not, but it's a useful starting point. If you're interested in that, there's another way to get a magnetization, of course. You apply a field, right? So what happens if I apply a magnetic field? I get something like that. I get paramagnetic behavior. I get a magnetization proportional to field out here. And then right about where the system is going to undergo a phase transition on its own, the susceptibility, the linear relationship between magnetization and field, diverges, okay? Remember that. But over here, that would begin to suggest
Sorry, what is on the vertical axis?
shear modulus, sorry, ratio of stress to strain, which I will also slightly modify as we go along. But that's a quantitative measure of rigidity, if you like. Okay, so again, we're down in these low, weakly connected structures. But if I add bending back in, that becomes another interaction, another term, which I will argue is very much like a magnetic field. Forget the symmetry aspects of a field versus bending, but it's just in terms of writing down some Hamiltonian, that's another energy term. Okay? I will ultimately sketch a Landau theory where bending really does appear as a field. Okay, so this begins to suggest a transition from a soft to a rigid response as a function of, in this case, connectivity. But the question we wanted to ask is, what about straining these materials? Okay? So what I'm going to do is bring another axis out here, focus only on these undercoordinated structures. This transition here is not relevant for us, but ask the question, what happens as a function of strain? Now, there's various reasons to believe that a system can become rigid, even if it's initially floppy as you strain it. Think about fabric, right? You don't build anything with fabric until you put it under tension. Fabric is a little too ordered, though, so I want you ultimately to think of a disordered structure. And I'll show a little cartoon to illustrate this as we go along. In fact, also in the polymer language, people have thought about strain or stress stabilized networks that are otherwise floppy. Also, there's connections, of course, in all this work to rigidity percolation work going back to the 80s. So,
Is rubber,
people like Mike
is
Ford.
rubber a good model?
Sorry?
Rubber,
Rubber's a terrible model.
terrible model for this?
Terrible model for this. Yeah. In fact, yeah. So any linear elastic theory for these collagen networks would be really bad. I'll show you several examples of that as we go along, including things like I ultimately want to show you that there's anomalous Poisson ratios, apparently, of some strange elastic phenomena. Rubber would be a very bad model, which is one of the reasons why we're interested in this. So trying to understand what is the physical mechanism. Okay, so what I'm going to do is go away from that linear shear modulus I talked about before, ratio of stress to strain, and I'm going to do Fung's thing. Remember those physiology experiments? I'm going to measure the derivative, or talk about the derivative of stress with strain. Yes?
Sorry, following up on Stefano's question, how about spider webs? Like sort of the
You're
opposite.
stealing a punchline.
Oh,
I'll show you a
sorry,
spider
okay.
web
Okay,
shortly.
okay.
Yeah, so hold on, yes. Spider web's an example of something which will get stabilized under extension. That's not the way the spider builds it, of course, but yeah, that's a good point. Okay, so right, so my claim is, inspired by various things, if I take one of these undercoordinated structures and come out on this axis here, notice avoiding any of these high connectivity intrinsically stable structures, we claim that there's a transition from floppy to rigid in that plane. And if that's true, the question we started asking is, what's the nature of that transition? Is it a transition, or is it some sort of vague analogy to a transition? No, I'm going to argue it's a real transition. Happens to be athermal, so you notice temperature is nowhere here. But it's a genuine phase transition, and it is second order line. It's critical. It's a line of critical points. Okay? That we didn't know.
I have a question.
Yes.
Why does Z change? I mean, using the
Z is not. So here I'm oh, hang on. You're talking about how could you change to Z?
how do you change? Yeah, isn't it a property of the medium unless you break the fiber?
Yeah, good point, and thanks for asking that. I should point out a big difference between these systems and other systems where you may have seen these counting arguments jamming of particles, right? Obviously, if I take particles, like grains of sand, and I compress that system, I not only change the density, but I create new bonds, new junctions, if you like, mechanical bonds between the particles that only support compression, not tension in that case. That's a way of changing Z. So you can undergo a rigidity transition changing the density of a particle system. I'm talking about networks, though, that have a fixed and non-changing connectivity, okay? And in that case, you can only move along a line. You would have to do a different chemistry to create a different network if you wanted to change this.
So each point along the red line is a different material.
It's a,
Well, no, not really, right?
so it turns out people can vary the connectivity of they know how to vary the connectivity of a collagen network by, you know, from about 3.2 to about 3.6 or 7. So you can vary it a little bit by changing the protocol. Yes?
Because I don't know much about collagen. So what is the nature of these connections?
So the image I showed before with the branch point, they really do branch. So collagen actually, you can think of the collagen fibers as a braided structure to some extent, and you can get branch points. But those branch points are pretty stable. So there is a plasticity, by the way, so I'm slightly oversimplifying when I say the connectivity doesn't change. But at least if the stresses are small, it's a fully reversible elastic response where you would return to the earlier state if you come back. So branch points seem to be pretty permanent in that regard. Or depending on what other, and you're going to tax my knowledge of collagen in general, you can cross-link it by various things. Glutaraldehyde is one that pops into my head, but that's a bad one because that really freezes.
There is
the
actually some chemistry of bond,
Yes.
like it's a bond of some sort. Van der Waals, or not necessarily the chemical, but it's there's something in between.
Non-covalent, by the way. All the bonding in these systems. These are assemblies of globular proteins, okay, that have non-covalent interactions.
Like you said that it's a braided structure, so like does it have perfect filaments or something?
Yeah,
like that?
so actually,
As
the structure of collagen is a very hierarchical structure. And so there's actually a sort of triple helix protofilament structure, to use the terminology of another biopolymer. I don't think that's what they say in the collagen literature. And then higher order braiding. So actually, this is one of the reasons why laying down collagen is so difficult. So it's we don't rebuild collagen very quickly. Anyone with sports injuries knows, right? Okay, so collagen is a tough system to make for that reason. Okay, so there really is something odd about my. Okay, sorry. What I was meaning to show was to take that structure I just showed you in the horizontal plane and flip it up to the vertical plane. So I want you to imagine an axis up here, which is strain. This is connectivity, and I claim that there's a line of transitions that goes something like that. So why would we think that might happen? Well, here's your spider web, right? So, and according, I don't know of a really smart spider that's figured this out and builds the webs this way. I don't think that happens, but turning the problem around, once the spider web is created, if I were to remove the connections at the boundary, if you like, if I weren't to strain it, apply stress at the boundary, and being slightly loose when I go back and forth between stress and strain, particularly if I've got a floppy system, I don't have a well-defined relationship between them. But anyway, this structure, if I remove that connection at the boundary, it would just collapse, right? Now you might say, oh, but that's a two-dimensional structure, and notice I have a four-fold coordination, right? Doesn't change anything qualitatively. You could go into this structure, which is basically locally four-fold coordinated, at least mostly, and you could cut 10, 15, 20% of the bonds. It would definitely no longer be four-fold coordinated on average. It won't change anything at all. All that would happen is you might have to move these, you might have to strain it more, okay? So I'll have to ask you to accept me on that, but that is true. Yes?
I'm not sure how the analogy works because here the connections are not Hookean.
They're not, exactly. So Hookean you should imagine as only the first approximation to some sort of tensile load-bearing structure. But you're absolutely right. The fact that they're Hookean in detail is not important. The fact that they support tension is important. There's another subtlety. These are actually not really hooky, and maybe this is what you're thinking, they don't support compression. So there's actually an asymmetry in the force extension relation. Yes, the opposite of, you can think of this as sort of anti-jamming. It's the opposite of jamming. That particles jam when you push them together. These fibers become rigid when you pull them straight.
Tensegrity.
Yeah, exactly. This relates to tensegrity structures in engineering too. Okay, so anyway, with that in mind, if we go back to this phase diagram, again, the claim is if I move vertically here, I should transition from floppy to rigid. I'm going to show you a little cartoon. I won't call it a movie. It's not a real, well, it's a simulation. It's a cartoon based on a real simulation, to the extent that the simulation is real.
Okay.
And I want to stop it. So let me back up slightly even. So what I want to do is I want to start, and again, this is just to illustrate the point. So I want to start with a triangular network, and I'm going to dilute it down to the point where it's sub-isostatic, under-coordinated, entirely floppy. I assure you, if you were to try and measure any sort of shear modulus for that system, it would be 0. And what I'm going to do is I'm going to make the spider web out of it by stretching at the boundaries. Again, that other way of constructing a spider web, if you like. The slightly misleading thing about this movie, though, is I'm going to keep the full network in the same field of view. So I am stretching it, and then I'm simultaneously changing the magnification. Okay? That's just so you can really see the network structure evolve. Otherwise, if I strain it really far, you'll just see a section there in the middle, right? Okay. So now let me start the movie, and I'm straining it. And you can start to see some rearrangements, right? It's no longer really part of a triangular lattice. In fact, it did a lot of rearrangements right before I stopped. Think critical fluctuations. The fluctuations are those non-affine or non-uniform deformations. Those play the role of critical fluctuations. Again, something that appears in jamming as well. Non-affine rearrangements in this disordered system. Interestingly, those rearrangements under strain are entirely encoded by the topology of the original network. So it's a quenched disorder that is responsible for this, and it's reproducible. Okay? Now, what I did is I stopped it right before crossing that boundary to rigid. So in any one of these states, right up to this point, it would continue to be entirely floppy, have no linear shear modulus. And if I strain it any more, you will start to find networks that have propagation of stress from one side of the boundary to the other. I would actually see a macroscopic shear modulus in that case. That'll show up as a red line. I don't know how well it will show up for all of you, but hopefully you can start making out some red. Ooh, it's not showing up very well. So I assure you that is red. Anyway, and of course at this point I've got a really stretched system, or if you like, a really drunken spider that made this web here. And it strained massively, so you shouldn't read too much into that. But basically, it has undergone a transition from a floppy to a rigid state. Yes?
Is this transition supposed to be dependent on the nature of the strain? So it's just uniform expansion, or am I allowed to do other stuff?
Good question. There's at least 3 common deformation modes one might study from a continuum mechanics point of view. Shear, simple shear. Simple shear. Uniaxial extension, or bulk expansion. You could, in principle, do any one of those. I will limit myself only to shear because of the connection experiments.
I didn't see the shear here. Okay.
So I'm asking you to generalize, if you like, from this picture for uniform expansion, that is something very similar happens under shear. There are some differences. So for instance, if I took that network and I compressed it, there wouldn't be a transition. Shear will stabilize under either direction of shear. So there are some differences, and in fact, the critical point will shift depending on what deformation. And we have explored that.
So are you pulling on random threads on the edge?
No, I'm just uniformly, it's either connected, where they hit the boundary, they're connected,
Yeah.
and I'm just pulling at the boundaries uniformly. Okay, so with that in mind, whoops, I wanted to show you experiments first. There. Okay, so this is actually the result. So this is a collagen network. Happens to be about 1 mg per mil. You may not think in those units, but let me just point out that's a 1/10% volume fraction. So this sample is mostly water, teeny volume fraction of collagen fibers spanning it, or forming a network that spans it. Important distinction there. That system is being strained, and it has a finite linear shear modulus because of bending. The critical point here is that red cross as it happens. And so what's happening here is that as you go into the rigid phase, you have more and more tension developing in the fibers. So you're transitioning from a bending response to a stretching response. That's another way to look at it. Okay, so now how would one analyze this? So this is in the upper panel, I'm just showing those experiments again, compressed a little bit. Notice the logarithmic scale. So notice that the stiffness, the differential modulus, or the incremental resistance to an additional deformation, you could say, is increasing by a little bit over 2 orders of magnitude as you move through that transition zone. It is a zone, it's not a precise phase transition. Think again of what would happen with magnetization at finite field. You wouldn't see an actual transition, but you'd still see the critical phenomenon if the field is low enough.
Is it not better to think about finite size?
No, finite size does something similar, but I don't need that here. That would even in an infinite system, this would apply.
But your real system, I imagine, is not very large.
Well, okay, if you mean real as in simulation, yeah,
No,
not so
real
big.
in your experiment.
Well, okay, so the mesh size of that collagen network I showed you before is about a micron, a couple microns. You could have samples at the scale of a centimeter would be a big sample, but certainly several millimeters. That's macroscopic, I would say. The structure is mesoscopic. That is important to know. There's a mesoscopic scale that's important right in between the molecular and the lab scale. Okay, so those are the experiments. This is the result of pretty simple simulations you can do either in 2 dimensions or 3 dimensions based on a random fiber structure. You can generate these structures in various ways. You can dilute lattice structures. You can throw down rods at random, at least in 2D that works, 3D not. And you find a very similar mechanical response. Yep.
This has bending now?
And these have bending, exactly. In fact, these different curves are with different levels of bending resistance.
So, like if in that picture, where are the fibers? How long are the fibers? Because now it's hard to tell where the fibers actually.
Yeah, so these little crosses are meant to note that there's a bending rigidity of that segment, but not between this and that. If that helps.
Okay, but it's not bending rigidity. The segments are straight. The gray segments remain straight.
Yeah.
Okay, so it's you're putting at the point of
It's
cross-linking.
a resistance to bending between segments of the network across a junction. There's various ways of modeling that microscopically, and it won't qualitatively change the picture. The transition in the values of moduli will change quantitatively, but not.
Has anybody done it with real bending?
Huh?
Has anybody done it with Euler beams?
Oh yeah, we've also done that with the so-called Mikado structure, where you just throw down rods at random in 2 dimensions. You just take Euler elasticity. Works the same. It happens to be computationally harder, so you can deal with smaller systems that way for purely technical reasons. So as you increase the bending resistance, you get a linear modulus which increases proportional. Again, think paramagnetism, right? Notice the increase in the stiffness right at the transition. And so what you might imagine thinking about this in terms of transition like paramagnetism, in the stiff, rigid, or ordered phase, you'd expect that the rigidity, loosely thinking of that as an order parameter, which is not correct in detail, would depend on the distance in the strain above that critical value, which is indicated by the dashed line. This is a log-log scale, so 0 cap k would fall off at minus infinity on this curve, okay? You might imagine, based on what happens for ferromagnetism, a power law behavior for that, with some exponent f for the distance from the critical point that is in fact observed. The exponent happens to be about 0.8 for critical phenomena people. This is a non-mean field exponent. That's another interesting aspect of this because jamming is mean field. Okay. And I would argue non-mean field is more interesting in the sense that there's subtle critical aspects. But that's a little bit in the eye of the beholder.
What would be the mean field?
Sorry?
What would be the mean field?
One. Sorry. Sorry. It's not a simple number, a simple integer or ratio, rational number. One happens to be what you get from a mean field argument here, in contrast with magnetic system.
And one more question. And what is the upper critical dimension for this?
So this has been a challenge. We just finally have an answer on that. So I'll get back to that.
All right.
Okay. So we actually know that now. So jamming systems are 4. But if that sounds trivial, because that's what things like the Ising model have, it's not that trivial. Because in this case, we didn't even have a good order parameter until recently. And jamming has an upper critical dimension 2. So other mechanical phase transitions that
throw away all the raptors and all the stuff you don't like.
Okay, yes, there's some I agree with you.
Right.
That is also still being sorted out.
Right.
But let's just say the behavior here is certainly different in detail.
If you look at the stuff that Paul has been doing with random organization, where they don't throw away the raptors, there it's also 4.
I guess I haven't seen that.
Yeah.
I'll have to get that.
Yeah, we can talk later.
Okay. So
Good thing we live in 3 dimensions.
yeah, most of us spend time in 3D. So, and then again, the analogy to paramagnetism and a susceptibility would suggest a function, a behavior, something like that, which I won't belabor. But what I want to get at is how to think about this a little bit more quantitatively in connection with magnetism. Again, still just drawing an analogy, which I will flesh out. Actually, I've already argued this should not be thought of as an order parameter. It's much more like a heat capacity. Okay, so it's another thermodynamic quantity that should show potentially singular behavior, not necessarily divergent, but singular behavior, and this does at the critical point. Okay, but anyway, nevertheless, you can still typically use a scaling theory like this, and so I'll start by talking about the magnetic.
I'll let you finish the slide.
Well, okay, so over here we have magnetization versus temperature. I'm sort of sketching that picture over there. And this T to the beta, where mean field beta is 1/2, would be the Curie-Weiss law from a early stat mech class you would have taken. That would be what you'd expect in the absence of a field. And if you apply a field, turns out you can capture things in terms of a scaling function like this, where H is the magnetic field and the diverging susceptibility is coming from the combination of that leading factor, T minus Tc to the beta and T minus Tc to the delta, if that function is a linear function, which it will be. And so what you can do is you can take magnetic data. My transition is looking really weird here, okay? There. This is magnetization as a function of field. Magnetization as a function of field for various temperatures. And if you simply divide magnetization by this factor here and plot it versus this combination here, all those data collapse onto a single function with two branches. This is ferromagnetic. By the way, these ideas go back to Whittam and others in the development of critical phenomena. I guess I'm not specifically citing that. This happens to be from one of the early analyses of this as a scaling approach for magnetic data. And this is the ferromagnetic branch where you've got a finite magnetization at low field. Field is the horizontal axis here. Actually scales up there. And this is the paramagnetic branch where I get a linear relationship between magnetization and field. So if something similar happens here for these magnetic systems with potentially different exponents, almost certainly different exponents, no reason to believe that this would be in the same so-called universality class for the critical phenomena people, audience, but in general you'd expect maybe different exponents. By the way, I will explain a little bit later where these scaling functions come from. It mathematically falls out from a deep physical observation, I would say. So then we should be able to take these computational data and do something similar. That's what we do. There's actually three different colors because this is three radically different structures. Mikado in 2D, that's rods just thrown down randomly, diluted triangular lattice, and some 3D data. So even in different dimensions, this seems to work. And all of them are doing very much the same thing. I've actually forgotten which color is which. I'll bet the blue is 3D just because the data are more limited.
Is this the fitted phi?
This,
Exponents,
yeah,
just
exactly. So we have allowed, we have chosen phi and f, two parameters, but for the family of curves simultaneously. So it's many different curves plotted together, but we've allowed those to be free parameters. And apparently a collapse works for values of, I did show you a direct way of getting f, by the way, in the previous plot. I showed you magnetization versus strain, and I'll show it again in a bit. You can independently get that one fairly easily. But indeed, the fit parameters here are really these two. Seems to work. And so at this point, I would say what we've done is we've answered the question, what's the nature of the transition? It is second order like, critical. What about experiment? So,
So this f and phi are they the same for different systems?
Yeah, that's, so whether or not 2D and 3D are absolutely identical is an interesting point. As I recall, we allowed, yes, we did that independent. They don't vary very much, and the reason you can see that is this upper branch. I should have pointed this out. This thing is in the way over here. Okay, I'm not quite sure what to do about that.
Move it.
There we go. Okay, so where's the critical point? If you do this analysis, notice you're dividing out by t minus tc to a power both axes. So the critical point is way off in the upper right-hand corner. That's one of the reasons why one would do these scaling analyses, because the singularity is pushed out to infinity, and so I get analytic behavior throughout the plane. So that's a convenience and an important aspect of this analysis. Yes.
A couple questions. First one is, how do you get two branches? Like in the simulation, what does it mean? Like sometimes it's one and sometimes it's the other?
No, we, yeah, so we can identify the critical point by removing the bending rigidity. At that point, we know, so basically turn it down to 0. And at that point, we know if you've got a finite modulus at all, I'm on one side of the transition. If I have no rigidity, if it's floppy, I know I'm on the other side of the transition. And then that sets the critical point. And then you just plot the data that's above that or below that.
But what do you vary? Because you told us we can only go in this direction, which is gamma. So it's
But I can vary the strain
for every
throughout.
sample, it's going to be slightly different, no?
No, I can vary the strain throughout. So take a given sample, strain it, just like temperature here.
Mhm.
I can take a magnetic sample, I can apply a field, go back and forth, apply a different field, go back and forth, etc. Same sort of thing here. There is a little bit of a subtlety about the critical point slightly shifting if you make a different network. Every time you
Yeah, that's
create a
what I
different,
mean, every sample is
so
different.
there is in fact so we do need to identify the critical point for each sample. There's a very slight variation because they're disordered structures.
And sorry, one more question, maybe more complicated, but gamma C, so like in terms of units, like
Dimensionless, so strain is just dimensionless. It's the derivative of displacement on one axis relative to another.
right, somehow it feels like, what does it depend on? Maybe you'll answer this, but like there's a length, there's something that controls
We
this.
know, I would say we don't have a full theory for how gamma C depends on network architecture, but we have scaling arguments, and so up to a prefactor, we can identify that functional difference. That takes more work, but we've done that. Okay, so here's the experiments. This is taking, I showed you one curve before collagen data. This is multiple. This is scanning a range. And the collapse is almost as clean. So for me, this is shocking. Look, this is a collagen network. This is a messy system. This is like a complex tissue that has a lot of quench disorder in it. And somehow these data are almost as clean as a solid state.
How did you pick the critical point if you can't remove the stiffness?
Yeah, so what we found from the computational work is that it's very close to the inflection point on the log-log plot. So it's a little bit of an empirical. It turns out if you shift it, it won't substantially change our estimates of the critical exponents. It'll mess up a little bit that critical zone. Right, so this is spanning almost an order of magnitude in concentration for collagen, and to my eyes, this is shockingly clean collapse. Yes?
I was wondering why you chose the concentrations that you did, like why vary by order 1 numbers and not like order 10?
I leave that to my experimental colleagues.
Sure.
I didn't do that.
Okay.
And what's gamma like a number? Like it's 20%, 10%?
Oh, yeah, it was on the previous plot, but it's about 20%. So the strength, the transition is occurring in these samples at about 20% strength. Okay, so, right, so the basic idea is we've got a transition. The transition only appears in the absence of this parameter that's always present, so I'll never see the transition. But if I can get close enough to it, I'll see the criticality in a region about that. That's very similar to, well, on a plot like this, what I'm saying is the critical point is here. I can approach it, but never quite reach it, okay? I probably won't have time, but one of the things that you can do is also look at an interesting connection between this and another kind of zero temperature phase transition quantum critical points, where you have a transition only at 0 temperature. You can come down to low temperature and see the criticality, and basically the same sort of mathematical framework, if you like, works, even though this is not a quantum system. Yes?
Could you remind what's the difference between kappa and gamma?
Gamma strain, kappa is bending rigidity. Yeah, so this is straining a given sample. This is coming from the original fabrication, if you like, of the network, or polymerization of the network. Okay. So let me show you how you might start building a baby Landau theory for this. Okay, baby is referring not to Landau himself, but to theory. Okay, so this is like a first step, and it's not correct, but it's a first step. It's not correct, not complete.
There was a talk in math today by a Russian mathematician. She said Landau only made 3 mistakes of there, which they've counted.
Oh, okay. So that's a pretty good success rate. Okay. So anyway, obviously a thing we have wanted for some time is to have a real framework to, and not just, having the simulations and agreement with experiment is great. It's a good starting point, but we wanted a theoretical framework. And this is brand new, unpublished. This actually, you can do much more than this. You can actually do I would say, a full field theory. You can start seeing how mean field exponents are corrected, etc. I won't go into any of that. But basically try to give you an idea that a simple toy model to see a transition of this kind is sketched in this little triangle I have at the top. These are, imagine two sections of a fiber, and I get a rigid system when I stretch it out. Okay? It's floppy like this, and when I engage and start creating tension in that fiber, it goes rigid. Okay? So that's the onset of the transition. That depends on the strain of the network, because that'll determine how much I displace the endpoints. And also depends on the angle that filament makes. And so what we do is we expand. So the bending rigidity enters like this. There's an angle difference between the current angle and what would correspond to a mechanically relaxed state squared. That's the first term in a bending description. We imagine a Hookean response here for the stretching of the fiber. Start turning that into an expression in terms of the strain, and I'll start calling strain a reduced temperature variable T, which is gamma minus gamma C. And so here's what our first terms in that Landau theory would look like. The theta dependence is just coming from expanding a cosine that appears in the trigonometry. So that's this looks a little bit like a Landau theory you'd write down for ferromagnetism, but it is different in some interesting ways. And in particular, just to show you, you can start understanding some of the behavior. Remember, I was describing this susceptibility-like behavior here, the increase in the stiffness as a function of T minus Tc. Well, so if you minimize this energy over the degrees of freedom, basically allow theta to relax to a minimum state, then you actually get an energy which goes like the square root of gamma minus gamma c, difference in strain. One derivative of the energy with respect to strain is stress. Two derivatives is stiffness. Two derivatives of that gives me an inverse gamma minus gamma c to the 3/2 power. I won't show you the data, but simulation shows a value of about 1.7. This is a mean field exponent. We can do more than this. We can start accounting for disorder, do a sort of Ginzburg-Landau theory, etc. For those, yeah. Obviously, that's the kind of thing you'd want to do. And Sihan, my student, has done amazing work on that. He's going to graduate soon and go work with Vincenzo Vitelli, and smart physics department should hire him. Really good. Okay. You can also start putting this in the context of real space renormalization. That's essentially, sorry, I guess we've already had lots of questions and I'm running late. So what I'll do is I'll just basically flash up that for those familiar with Kadanoff's real space renormalization picture, that beautifully explains why in physical terms you'd expect a so-called homogeneous function for in this case, the elastic energy, more generally the free energy. And so that starts allowing you to determine all those critical exponents that appear in terms of two fundamental exponents, x and y. All the others should be combinations of those, plus the dimension. And that seems to work. And this is basically just to show you that indeed the fluctuations diverge as you go through that critical point. Those fluctuations are those network rearrangements that were occurring in that cartoon I showed you right before I stopped. Those play the role of the fluctuations. They're not thermal, though. This is entirely a thermal system. And you can ask the question, what happens with temperature? And basically, you wind up with temperature also stabilizing these systems. We know that you can take a mechanically floppy system and stabilize it with temperature. That's known as entropic elasticity, right? You take a perfectly flexible, mechanically flexible polymer chain, turn on temperature, and you get an entropic resistance to stretching because there's fewer states in the stretch state, lower entropy. Okay? But that mechanics has to be proportional to temperature because the free energy has a term which is minus Ts. And if it's entropic, the mechanical quantities are all going to be proportional to temperature. Well, that's what I expected. It's actually T to the 0.8. Another anomalous exponent, or if you like, anomalous entropic elasticity. For the two-dimensional, we don't really have 3D yet, but at least as you go away from a polymer chain to a 2D structure and start allowing that to thermally fluctuate, you get an anomalous response.
Numerics.
That's based on simulation, yes. Okay, I think I should end there and not get to the Poisson, the strange Poisson ratios that are also observed. But if there's interest, I'm happy to talk about that because they're also, you understand them in terms of the same phase transition. So thank you for all the questions, though.
Thank you, Fred.
So what is the upper critical dimension?
4. So so we think so what happens there is, so Sihan has been able to actually calculate the corrections to mean field. And by the way, the order parameter, don't think that angle is an order parameter. You actually need a correlation function involving angle. So it's a little bit more complex, but not much. But when you do that and you start accounting for the disorder, so if you might know that to really account for disorder, you can't just, it's not even a renormalization group framework. You might need something like replica symmetry breaking, stuff like that. So we're not anywhere near there, but we do at least have the first order corrections, square, quadratic and fluctuations. By the way, when I say fluctuations, what I mean is disorder. So the disorder enters in that. Huh? Yeah, the quench disorder. So if you try and average over that, the first corrections give you exponents that are different from the mean field ones. Importantly, they are in the direction of what's observed computationally, so it makes sense. And they go to the mean field values in D equal 4. Yep.
So a lot of our applications of collagen involve the system under load, like our knees and stuff like that. So were you only talking about the system under tension, or should I also think about this under
shear? And of course, see collagen. So you compress collagen, and it actually has a matrix of hyaluronic acid in it as well, at least in the example, like the examples you're talking about. And so, and by the way, that is a much finer polymer meshwork, and is itself, to a very good approximation, incompressible on the timescales you're interested in. And as you load that matrix is topologically constraining the collagen matrix. So that collagen network is also incompressible as a result of the hyaluronic acid. And so even though you might be loading it, you're shearing it. In a volume. So shear is informative for what happens for loading real tissue. I didn't see a hand. Here, yes.
Could we flash the Poisson ratio just to see what?
Yeah, sure. So it's been known for several years that so Poisson ratio. So in short, take I'll start with an incompressible material. Take an incompressible material, strain it 10% along one axis, and it will contract by 5% along the two transverse dimensions. In 2 dimensions, it would have been 10% by the one transverse. Okay, so that preserves volume. Most materials are pretty close to that. There's exotic materials that have negative Poisson ratio. You pull it along one axis and expand in the other. Okay, that's fun, but not what I want to talk about here. So if you take tissue, people have known for at least 10 years now that you can extend some, actually, I like the second example even better. Here, this is a collagen system. This is strain in longitudinal stretch in this is 5%. The dashed line there refers to the incompressible condition. It's the lateral reduction in extent as I extend it horizontally in this case. And notice this blue line deviating hugely from that. That system has expelled 90% of the water and contracted to only 10% of its original extent, with a longitudinal strain of only 5%. Poisson ratio, well, people have reported Poisson ratios of 10, and that's dangerous because the Poisson ratio is really only defined in the linear elastic regime. But what's interesting is this is happening at 1% already. So I would say it certainly is understandable that it would be called an anomalous or violating Poisson ratio. The upper limit happens to be incompressibility, by the way. No material would, let's see, no material, straight. Yeah, you wouldn't expect a material under any extensional strain to reduce its volume. Only possibly increase. That system would be unstable. So what we showed is that transition is actually governed by that effect appears coincident with that critical strain that I talked about. So it moves right along that boundary that I mentioned.
But it is based on pushing water out.
No, well, so in this case, we do simulations on essentially networks in vacuum. This is not real.
So your computer does not?
We don't have water in it.
In your computer, no?
I had a question about the temperature numerical results you showed at the end. So when you're including temperature and the effect of elasticity, maybe you partly said this, you're changing the springs to have the individual springs to have a different stretching that depends on temperature, or you're quenching in randomness, or you're allowing the angles to change?
So all I'm doing is taking Maxwell and going to finite temperature. That's all I'm doing. Just take the original Maxwell picture of Hookean springs, add thermal fluctuations. I was shocked to learn no one had done that, to my knowledge, until about the 90s. Plischke did some work on that. And I'm not talking about Gaussian chains, by the way. I'm just talking about Hookean mechanical springs and adding thermal fluctuations. Even that Plischke paper, though, they just simply assume that it's entropic elasticity here proportional to T, and they don't analyze it. And I told my postdoc, Matthew Dennison, repeatedly, it's got to be entropic, it's got to be linear in T. Has to be, right? And he kept saying, no, it's not.
But you were saying since you're doing numerics, you're saying you do simulations of springs?
Monte Carlo simulations of Hookean springs at finite temperature.
Okay, well, to be fair, as chemists, we do like springs all day long, molecules.
Sorry. You're right. What I mean is looking at this in terms of the mechanics of the Maxwell.
But does are the angles thermostated also? There's no the bending is also temperature dependent, or only the stretch?
The nodes are basically degrees of freedom. So angles definitely fluctuation. No, I know I'm not doing justice to molecular dynamic simulations and Monte Carlo over the years. What I mean is, from this perspective, basically trying to ask the question, what happened to this Maxwell counting argument at high temperature?
I have a very naive question. I guess that in your simulation, your model, you assume that the connectivity is constant.
Yes.
And what about the experimental system?
So the reason we believe that is entirely reasonable is they can reduce the strain back to 0 and reproduce the same curve.
There's no damage.
If they go to high stresses, it will be damaged, and then it'll go to a different curve. So they know when they get plasticity or some sort of irreversible deformation, and that is precisely why these data are so limited in the stretched branch, because the system is failing there. And so they only use the data up to the point at which it's fully reversible. That's important.
And would it apply in a network where you keep the connectivity, but you have cross-link exchange? You see that you can flow.
We could do that. We haven't. Yeah. So it turns out a lot of biopolymer systems, especially the intracellular ones, like the delta networks that are active, they're actually all transiently cross-linked. So the cross-links are, themselves dynamic. That's an interesting rheology associated with that.
They get that developed, the people can back in here.
Okay, sorry I ran way over, but I
Yeah,
enjoyed all the questions in the
That's
in the
not
intro.
your fault.
No, it's fun.
As a matter of fact, I still have some questions, but
I would expect nothing else.
Okay, very good. After your talk, I always have lots of questions. So let's thank Fred once again.